With that, bright idea born.
The inventive genius whose fantastic mind had formulated the magic of the incandescent light bulb.
No great scholar? That's Thomas Edison he's talking about, the inventor of the light bulb.
Once dependent on carbon filaments that burned dimly and failed within weeks of installation, the electric light bulb by the early 1910s was undergoing a fundamental transformation. One driven not by a new invention, but by a materials breakthrough that made an existing idea finally work at industrial scale. The result was a product so reliable and affordable that electric lighting moved from the homes of the wealthy into the daily lives of ordinary people within a single decade. Manufacturing it, however, was considerably less straightforward than switching one on. This video will take you inside light bulb manufacturing in the 1910s to uncover exactly how raw tungsten powder, glass, and brass were transformed into a finished working lamp, why each stage demanded precision, far beyond what most consumer products of the era required, and how the production methods developed during this period established the foundation for electric lighting as a global industry. Right now, let us explore this remarkable manufacturing story together. For the first 2 decades of commercial electric lighting, most incandescent bulbs used filaments made from carbonized bamboo or cellulose thread, materials that could withstand the heat of electrical resistance long enough to produce light, but which burned out relatively quickly and produced comparatively dim output. The search for a superior filament material had focused on tungsten for years, given its extraordinarily high melting point of approximately 3,422 degrees Celsius, the highest of any pure metal, but processed tungsten remained too brittle to be drawn into the fine wire a filament required. That problem was solved in 1909 when William D. Coolidge, working at General Electric's research laboratory, developed a method of processing tungsten powder through sintering and mechanical working that produced a ductile, drawable wire. By the early 1910s, this process had been scaled to industrial production, and tungsten filament bulbs were replacing carbon filament designs across the market. Interestingly, a tungsten filament bulb of the 1910s produced approximately twice the light output of a carbon filament bulb consuming the same electrical power. A difference significant enough to drive rapid market adoption within just a few years of commercial introduction. From that point, every bulb began the same journey, starting as raw powder and ending as a finished lamp ready for the consumer market. Every light bulb manufactured in the 1910s began its journey as a collection of carefully selected raw materials, each chosen for specific physical and electrical properties the finished product required. Tungsten arrived at the factory as a refined powder, produced from wolframite or scheelite ore through a series of chemical reduction and purification stages that removed metallic impurities capable of compromising the mechanical properties of the final wire. Lead-in wires, the conductors carrying electrical current from the base contacts to the filament, were made from copper or nickel-iron alloys selected for their conductivity and thermal expansion compatibility with the glass stem they would be sealed into. Nickel-iron alloys were particularly valued because their expansion coefficient closely matched that of the glass used for stems, reducing mechanical stress at the seal during repeated heating and cooling cycles. The glass envelope was produced from a carefully formulated lime soda glass composition chosen to balance workability at furnace temperatures accessible to 1910s equipment with sufficient thermal and mechanical resistance for lamp service conditions. Brass for the screw base provided the standardized Edison screw connection already installed in homes and commercial buildings across the country. At this stage, incoming materials were inspected against specification, tungsten powder lots sampled for purity, glass tubing checked for dimensional consistency, and lead wire stock verified for diameter uniformity. Only materials meeting the required standards advanced into the production sequence. The production of the tungsten filament was the most technically demanding stage of the entire manufacturing process. Verified tungsten powder was first pressed into rectangular bars using hydraulic presses, then sintered in hydrogen atmosphere furnaces at temperatures exceeding 1,000 degrees Celsius, a process that fused the powder particles into a solid, coherent mass without fully melting the metal. The sintered bars were then worked mechanically through a sequence of swaging and forging operations, progressively reducing the cross-section while improving the internal grain structure of the metal. This mechanical working was what made Coolidge's process distinct. It transformed inherently brittle sintered tungsten into a material capable of further reduction without fracturing. Following mechanical working, the rod was drawn through a series of progressively smaller tungsten carbide dies, each pass reducing its diameter incrementally until wire finer than a human hair emerged. Thin enough to be nearly invisible against a white background, yet capable of operating continuously at temperatures exceeding 2,500 degrees Celsius during lamp operation. Once the wire reached its final specification, it moved directly to the winding stage. Finished tungsten wire was transferred to winding machines, where it was wound onto mandrels, thin metal rods of precisely controlled diameter, to produce the coiled or straight filament geometry specified for each lamp type. General service lamps of the 1910s used either straight filaments or the squirrel cage configuration, in which multiple straight sections were connected in a three-dimensional framework that distributed heat more evenly during operation. Winding pitch and coil diameter were held to closed tolerances, as dimensional variation in the filament directly affected the lamp's electrical resistance, light output, and operating life. Once wound, filaments were mounted onto glass stems in an operation called mount making. Workers positioned the filament between the lead-in wires and secured each connection point, then attached small support hooks at intermediate points along the filament length to prevent sagging during operation. The completed mount, filament, lead wires, support hooks, and glass stem assembled as a single unit, was inspected before advancing to the next stage. One fascinating detail is that mount making in the 1910s was performed almost entirely by hand, with workers assembling individual components under magnification across hundreds of units per shift, a standard of repetitive precision that few other consumer products of the period demanded. Glass envelopes for incandescent lamps were produced either by manual glass blowing or, increasingly through the 1910s, by semi-automatic ribbon machine equipment that significantly increased output rates. The ribbon machine fed molten glass between forming rollers, then used compressed air to inflate individual glass portions into molds moving in synchronization below, producing finished envelopes continuously at volumes manual methods could not approach. In both hand and machine production, formed envelopes were annealed, slowly cooled through a controlled temperature gradient in a Lair furnace, to relieve internal stresses that would otherwise cause the glass to crack during handling or lamp operation. Annealing times for standard household lamp envelopes of the period typically ranged from 20 to 40 minutes. Each finished envelope was inspected for wall thickness uniformity, dimensional accuracy, and surface defects including bubbles, cords, and thin spots before advancing to sealing, ensuring that only structurally sound envelopes entered the more labor-intensive stages of the production sequence. The completed mount assembly was inserted into the glass envelope and positioned centrally before the neck of the envelope was reheated and collapsed onto the glass stem, forming an airtight junction between the two components. The integrity of this seal was critical. Any leak path, however small, would allow atmospheric oxygen to enter the envelope during operation and oxidize the tungsten filament within seconds of the lamp being switched on. Following sealing, the lamp was connected to vacuum pumping equipment through the exhaust tube incorporated into the glass stem. Pumps evacuated the envelope to the lowest pressure achievable, with equipment available in the 1910s, removing almost every trace of air from inside the sealed bulb. Early in the decade, most lamps were sealed under vacuum at this point. As the decade progressed, manufacturers introduced nitrogen-filled gas at subatmospheric pressure, a development that reduced tungsten evaporation from the filament surface and extended operating life compared to vacuum designs at equivalent temperatures. Argon, which offered further performance advantages, became more widely adopted in subsequent years as gas-filled lamp technology advanced beyond the 1910s. The exhaust tube was then tipped off, melted closed, completing the sealed lamp body and preparing it for the final assembly stages. The brass screw base was attached to the sealed lamp body using an electrically conductive cement that simultaneously bonded the base mechanically and connected the shell contact to the outer lead wire. The center contact pin was soldered directly to the inner lead wire, completing the electrical circuit from base contact through lead wires to filament and back. Each connection was verified before the lamp advanced to testing. Finished lamps were connected to standardized electrical testing stations that measured light output, electrical consumption, and filament continuity against specification. Lamps producing output outside the specified range, drawing incorrect current or failing to illuminate, were removed from the production lot and analyzed to identify the responsible process stage. Lamps. Meeting all specifications were cleaned, labeled with wattage and voltage ratings, and packed individually into paperboard cartons for shipment. By 1914, General Electric alone was producing tens of millions of tungsten filament lamps annually, with additional output from Westinghouse and a growing number of licensed manufacturers. Retail prices for standard household lamps had fallen to approximately 25 cents per unit by the mid-1910s, placing electric lighting within reach of the broad consumer market for the first time. Every lamp that reached that market had passed through the same sequence: powder to wire, wire to filament, filament to mount, mount to sealed envelope, envelope to tested and labeled finished product. A chain of precision manufacturing operations that, in the 1910s, still relied substantially on skilled human hands at nearly every stage. Whether those hands found the work rewarding or simply repetitive after the 10,000th filament of the shift is a question the production records of the period did not think to document.